Okay. All right, disease propagation. What does it even mean? Let's think about that. So we will have healthy people, right? We'll have healthy people. We will have people who are sick. And then people who are sick, they will be contagious and they will transmit the disease to people who are in contact with them. And we will interpret this graph for now as a graph of contacts. So let's say that people who are connected with an edge, they like see each other regularly. So how will the disease propagation happen? Will it be that every person is like the moment you get in contact with a person who is sick, you get sick as well? Probably not. Probably it's a probabilistic thing, right? Because you may not, it takes some time, it takes some effort. Kind of for a more contagious disease, it may be almost instantaneous, but still there is some probability involved, probably. So if you're connected to a person at each time step, we will just toss a coin. Not necessarily 50-50 coin, but we'll roll some dice. We'll look at some probability. So we will probably have probability of transmission as one of the parameters of the model. If it's high, it's close to 1, it's like measles. If it's low, it's close to 0. It's like what disease is hard to get? I don't remember. Well, yeah, you can look it up. But yeah, we'll have this probability of transmission. So we'll have healthy people, and with certain probability at each time step, so we'll have a time loop that will run for a while, either until everybody is sick or just for a certain number of steps. We will allow the disease to propagate. So, people actually modeled that, as you can imagine, for quite some time now. And one place where we can read about that are those compartmental models in epidemiology, which is not exactly what we are doing. Here, people are kind of writing differential equations. They just have a pool of healthy people and pool of sick people and some speed at which people go from being healthy to being sick, or from being sick to being recovered. But the interesting idea is that if you look at that, we don't have to read all of that. See, there are some differential equations. But the greatest idea that we need to lift from here is that we put people to these categories. So there are some states that every person may be in. And in this case, these are some variables, the number of people within the population that are in each of these bags. But for us, this will be states of those elements on our graph. So each node, if each node is a person, each person may be healthy and susceptible, or they may be sick and infectious. And this is like two models at a minimum, right? Healthy and sick. But we can add more. We can have recovered. Let's see what other options are there. We can have, oh, they can go back and forth. So maybe when they recover, they don't actually have immunity, right? The way why recovered may be different than susceptible than like previous healthy. It's in case, so it's useful if they don't get sick once again. So if there is immunity, then we do susceptible, infectious, recovered. If we have, if there is no immunity, they can oscillate between susceptible and infectious. This is too fancy, something maternal, whatever. Oh, look, there may be a carrier, or people may be exposed, or animals, or something, plants. They can be exposed, so maybe they're susceptible, but then they're exposed, and they like linger at this state for a while before they become infectious. What else is there? Vaccination, modeling vaccination. Well, you can think about that. What other options are even on the table? Dead is another option, right? Maybe some of them die. Maybe some of them acquire immunity, some of them don't. Maybe you differentiate between those people who are infected and spreading the disease, and those who are so sick that they kind of lie at home and no longer spread the disease. We'll see. But we know what the options are, right? So let's go here and try to sketch it. So we'll have time. That's one thing. A loop over time. This is my, it's not even pseudocode, it's just logic. A loop over time. At each stage of the loop, what do we do? Infectious people can infect other people, right? So one option is go through all infectious sick nodes that are sick, which is infectious, the same as an infectious. So for each node that, so we identify, we have a list, maybe we keep a list, so we just go through all nodes and pick those that are infectious. So for each infectious node, so instead of go through, let's write for each node that is sick, infectious, what can happen? It gives disease, the bug, to one of the other nodes, right? It's connected to. So how do we do that? Is it that it always gives disease to only one node? Not necessarily, right? So for all nodes, for all healthy nodes that are connected to this sick node, it can give the bug to all nodes it's connected to, if maybe, right? If the probability of spread is high. So we pick each sick node, we look all healthy nodes it's connected to, and for each of those healthy nodes, if like roll the dice, if okay, with some probability, in fact this neighboring node, right? That's pretty much it, and we'll go through that a loop over time. We'll go through that. We will either go a certain number of steps, I'm guessing. Let's set a highest number of steps, or if all nodes are sick. Also, that's another reason. If all nodes are sick, there is no point to run further. Well, let's keep it like, well, whatever. Let's keep it like that for now. What else do we do? This will work, however, one thing that's absent is what are we even measuring? So how will we tell that the model works? Okay, for now, let's implement that. And let's just look at which nodes are sick and which nodes are healthy, right? Okay, which actually leads to a problem. Our visualization for now doesn't tell us which nodes are sick, which nodes are healthy. Okay. How do we make it happen? Let's look at our plotting thingy. So our plotting thingy is, it relies, this method plot that we have, it relies on network X module, and it uses this an X draw something something command Kawaii, which is a particular spatial distribution of how to arrange the nodes in space, but it's this family of draw functions with different layouts. So network X draw. Let's see whether we can color markers in some way. Drawing. We need to look at that. See network X, draw network X for description of optional keyword. Where is it? This one. Okay, what can we do? We can give positions, arrows, we don't care, with labels. Labels are not ideal. We want colors. Ideally, we want like healthy to be blue and red to be like sick to be red or something like that. It is node. Okay, node color. Oh, look at that. That's great. Color or array of colors. So it can be a single color or a sequence of colors with the same length, and each color may be a string or RGB, tuple of floats from 0 to 1. It can also be numerical values, and then they will be mapped to colors using some map. Good. Okay, node colors. So node color can be an array of tuples, each tuple being an RGB, and the length of the array should match the number of nodes. Let's go and try to implement that. Plot self. Node color equals colors. Colors are not defined yet. Colors. We need to add colors, and colors will be dependent on the state of the node. Do we even have the state of the node yet? Let's look at that. We have nodes, and nodes are just, it's a dictionary. Okay, we don't have it, right? The only thing that the graph knows about itself, the only property that it has, the only variable that it carries around, this object carries around, is the dictionary of edges, of what's connected to what. So we need to start with adding something here. Self values equals list, empty list. Good. So we have values now. And for now it's empty list. But when we add a node, we need to add a value for this node. So add node is a good place to change that. Add node. Let me change values to val. That's a shortening that people often use. So when we do node, we will also have val, and the default value will be none or zero. None or zero. Like none is nicer, but maybe because we know how to use it, let's use it. Let's because we're building it for ourselves. For now, let's make it 0. So value equals 0. If node in self dict, do this. Oh yeah, that's a little bit of a problem. Okay, let's make value not a list. Let's make it a dictionary as well. A dictionary as well. And when we add a node, we will do self val node equals val. Yeah. Yep. Good. Okay. So we have a default value. So just us adding that shouldn't change anything. It should be still working. Even our old uses of this class should still be working. But now we can assume that there is a dictionary that contains values. And I had to use a dictionary, not a list, just because I use, when we add nodes, we add them via kind of like, we add nodes with a certain key, and keys, we usually use numbers here, but these numbers don't have to be consecutive. We can use strings. just the way I implemented it so far prevents me from just keeping a list or a NumPy array of values. I have to use a dictionary. But here, when we plot it, we will actually have to make an array. So, okay, we will have to translate it from this dictionary of values into a list of values. And just to be clear, what I'm doing now is kind of nice to have. It's not something that we have to have. I'm doing it only so that we could have nice visualizations. Make sense? Okay, so we need to create a list of colors for each node. Sure. For, we'll have to go through all nodes. For all nodes are stored, like nodes are keys of this dictionary. So can we somehow iterate through a dictionary? Turns out that we can. Oh, we did it before. Like look at this line, for example, for node, comma, links in self dict items. So we'll need something like that here. For node, comma, value, val, in self, what's the name of it? Val, items. This thing will iterate through all nodes and will extract values of each node. And so far, all values are 0. So let's create a list called colors. Colors equals, let's first make let's make a list on NumPy array. Okay, let's do NumPy. Doesn't matter, but NumPy is fine. Zeros, how many? The same as the number of nodes. How many nodes? Was the easiest way to calculate it, like length, self value. I don't like this val anymore. I'm sorry. I will have to go and to replace it with values. It just, so I want this one to be values. I want it to be plural so that it makes sense. Like this is semantics, but I want this one to be plural. And one value I will still use val. So this way, when you see that the variable is called self values, you know that it contains some sort of values, and because it's plural, you know that that's a list. It's just a healthier name. Okay, so for node val in self values items, colors, which one? Node. Oh gosh. Just a second, let me think. Get nodes. Okay, so they should go in the same order in which the nodes. So the problem here is that the colors should go in the same order in which the nodes go. And the nodes are provided to network X here by the command get nodes. And get nodes just returns a list of keys. Can we be sure that if we do this part, the values will go in the same sequence? It doesn't feel right. Okay, let's do it slightly differently. So let's go back here and do nodes equals self get nodes. This is now a list of nodes. Then we do add nodes from this list. And then here, let's do for node in nodes. So we will reuse the same list that we've already generated. That way, we will guarantee that the sequence is the same. And No, not even that. We will do the following. For I in range length nodes, so we will count. We'll go through the list of nodes and we will count where we are. We need an integer. We can't use a node because colors is a vector. We just need to write something into 0th element, first element, and so on. So colors I is a color of this node. Where are colors stored? In self values. What node are we talking about? Nodes I. So this way it should work. And if we do that, we will have a list of numbers. Yeah, it should work. It's okay. It's not like we haven't specified what numbers they are, but it should work. Let's add the plotting functionality. Let's just test it. Does it still work? Nope, doesn't. Length. Yeah, of course not length. It's called len. Okay, it works. The color has changed. It used to be green, now it's kind of black. But it's okay. All right. So let's go here. Let's rerun this thing. Now it's purple. It's all right. Purple. Really deep, really dark purple. Okay. Now let's try to. We need to test that. So let's try here in the first, like when we test this class in general, let's change the color of one of the dots. G values say like the value of the, oh lord, that's a dictionary. It's okay. Of the 0th node, no 0, let's make it 1. Aha, it works. The colors are really sad though. Look, it's purple and yellow. Yellow is hard to see. I don't like that. Okay, change of mind again. Change of mind. Let's make it pretty. I'm not sure. Well, I always spend too much. I personally, as a person, I always spend way too much time in making things pretty, even when it leads nowhere, just for aesthetic purposes. So I'm not sure that's something I should like model for you guys, but that's what I do. So I just cannot. I want it to be red and blue. I'm sorry. So let's define two constants. Red is a tuple RGB, so it's 100. Blue is RGB 001. Maybe even let's do 0. Like let me go for some weird bluish, greenish blue. That's slightly off, slightly darker. Okay, red and blue. These are two constants for colors. And then colors will be a list, no longer a numpy. Oops, didn't work. No longer a numpy thingy. And then instead of changing the value, I will do append. So I will add values to it one by one. But what will I add? Either red or blue. And I will just have a conditional here. If this thingy, if the value is 0, then please append blue, else colors append red. Yay! It works. Okay, so in fact it will. I don't like this blue. No, this is ridiculous. I know. Better. So now healthy ones will be blue. Sick ones will have a value of 1 and they will be red. Good. time to make a propagation plot. Okay, let me stop the recording once again.